अब इस वाली रिवीजन का पर्पस ये है, वैसे तो हर चैप्टर, एवरी चैप्टर आई हैव पुट इन माय ऑन माय चैनल, every chapter is there and it will be a quick revision. Also I have shared two parts of the videos which are very quick video, and the two videos cover the whole syllabus. लेकिन interactive revision का benefit ये है that you can ask and I can ask and we can quickly revise the main concepts. We have selected superposition. Superposition is considered to be the most effective chapter in our course, considered to be the #1 chapter in our course. But frankly speaking, in all the recent past papers, superposition have not made any big problem. Dynamics is somehow more challenging, more disturbing in that sense कि उससे ज़्यादा dynamics ने problem किए हैं. So let's start this chapter, superposition of waves. The one-liner for the chapter is formation of standing or stationary waves. So I'm putting the first concept, that is the introduction. What is the idea of superposition? It is the meeting of two waves end to end, and it is called superposition. The example which I normally give here is putting our two hands, and our two hands are complementary to each other. If we put our two hands on each other, our hands superimpose on each other. So superposition is basically the idea of two waves meeting side by side. Principle of superposition. This is the first thing which always come in the paper also. So when two waves moving in the same medium with the same speed, they meet at a point, the resultant displacement is the algebraic sum of the individual displacements. So when two waves are moving in a medium, and they meet at the same point, and they have a common displacement, they have a common wavelength. When two waves moving in the same medium with the same speed meet at a point, the resultant displacement is the algebraic sum. So look at these two waves, and these two waves are the above example is they are meeting crest to crest. This is called exactly in phase. And the second example is meeting out of phase. It means one is trough and one is crest. So the resultant displacement will be subtracted. And in the above example, the resultant displacement is obtained by adding the two displacements. So look at this example, and I will ask a question. First, you look at this example. Now my question, why it is necessary that the wavelength of the two waves should be the same.
Is it because if the wavelength is different, there will be a resulting displacement?
Good. And the point is there that the first condition is there. Meeting two waves cannot superimpose, like our two hands are actually complementary to each other. They are exactly the same. So remember that example that you put your two hands on each other. Why this superposition? Because they are complementary to each other. But if the two hands are of different size, the first condition fails. The first condition fails, that superposition is not there. So when superposition is not there, there is no question of principle of superposition. Stationary or standing wave, the chapter primary topic, the chapter actually based upon this. Now, we had studied that what are stationary waves, the waves which appear to be stationary, originally they are moving, but they appear to be stationary because they form a loop, because they form a loop in which energy keeps on jumping within the system, but they are not progressive. They do not transfer energy out of the source. They keep the energy with them, and they keep on transferring energy within the loop. This is called a stationary wave. And I always remind people of that rubber band example, which is quite famous, that if you stretch a rubber band and so you can see that these are called stationary waves. Stationary waves are categorized in different ways. For example, stretch strings like guitar, microwaves like microwave oven, and air columns, which are called musical instruments. These are the famous examples. Let's start with stationary waves in stretched strings. Guitar is the example. Now, this is a string and you pluck it from the center. The string begins to vibrate. The string begins to vibrate. It moves up and down. It moves up and down. And as it moves very quickly, it forms an apparent stationary phenomena. Actually, the waves are switching, but the incident and reflected pulses are progressing left to right, right to left. So they superimpose on each other, and this apparently form a loop. Formation of stationary wave. This is how we discuss the formation of stationary wave. This is a very famous question. This is a very famous question, that how we form a stationary wave. When we were doing past papers, we come across this question many times. So now I am putting my second question for today, that how a stationary wave is produced.
Sir, I think as you told us before,
A very famous question, and we saw its examiner report also, that a stationary
say unstationary waves form waves with equal sorry
but you speaking
equal wavelength.
a bit loud, is formed due to
Interference between two wavelengths.
Due to superposition of two progressive waves. What are those two progressive waves? Incident and incident and the reflected pulses. This is their favorite question, and they have asked this question many times. They have asked this question many times. I'm sorry, I lost the screen, and happens when exams are close. So even technology is okay. I hope you can see the screen again. A stationary wave is formed due to the superposition of two progressive waves, incident and the reflected pulses. To understand this, look at this diagram. The reflected pulse and the incident pulse, they superimpose on each other. Now, how we talk about speed of a stationary wave. Yes, how we talk about when it's a stationary wave in physics, when something is a stationary, it should have no speed. But technically, the incident and the reflected both are moving. So it is the speed of the incident and reflected waves. They both are moving. They both are moving they both are moving at the same speed. So this is the concept. We established this challenging concept, and I remember, I think, Zen, you were there when we were discussing this question, and examiner was saying that, and examiner was saying that many people do not mention progressive waves, incident and reflected. They just mentioned the two signals. Now, node and anti-node, a very famous concept. This comes every year. When this chapter comes, normally this chapter is coming as a club. These two topics are coming together. And I think this chapter and the previous chapter, they both come together. Now, what is node and what is anti-node? Node is the point of zero displacement, and anti-node is the point of maximum displacement. So when a stationary wave is formed, there are some points where the displacement is maximum, it is anti-node, and there are some points where displacement is zero, it is node. So you have to learn this. Node to node, it's lambda by 2, and 1 lambda is as 2 pi radian. So lambda by 2 is pi radian. So the phase difference between two successive nodes is always pi radian. Phase difference between two successive nodes is always pi radian. So look at this screen carefully. And this is something to learn. This is something to learn very strongly, because this is a problem to remember, that the game of phase difference is always a very big challenge. So what concept I told you? phase difference between two nodes or two is always pi radian, and it should be a memory that pi radian is equal to 180 degree. Now, this is the formation of a stationary wave. There is a reflected pulse, there is an incident pulse, they superimpose on each other. This is how a stationary wave is established. This is how a stationary wave is established. We have an incident pulse and we have a reflected pulse. They meet and they form this. Can you tell me, I put my question here, that what is the resultant displacement when a stationary wave is formed? What is the resultant displacement? Look at the screen. What is the resultant displacement when a stationary wave is formed?
0.
0. Good. This is a very famous question. Twice, when it came the first time, the majority people couldn't understand this concept that how displacement can be 0. Actually, when a signal is moving up and down, and it is traveling the same distance above the line and below the line, the resultant displacement would be 0. Apparatus to form stationary wave in a string. Look at this apparatus. I have a string and I'm hanging a load from one side. There is a peg on the support, and I can increase the load to increase the tension. This is the real apparatus. I have placed some weight signal generator and vibrating. It is an electrical vibrator. The vibration will produce successive node and anti-node. The separation between two successive node and anti-node is lambda by 2. Now, you can vibrate something in different loops. 1 loop, 2 loops, 3 loops, and then it can go on. Now see the case number 1, which is the fundamental harmonics, and we are vibrating it precisely in 1 loop. When we are vibrating it in 1 loop, the total length is lambda by 2. The total length is lambda by 2. L is the length of the string. If you have a chance of playing guitar, then it is the first pluck. When you pluck it first time and you hear a very starting sound, it is 1 loop. Now L is equal to lambda by 2. Why L is lambda by 2? Because the total separation is between two nodes. Separation between two nodes is always lambda by 2. Separation between two nodes is always lambda by 2. So this is the first case. Now, my question comes, why we call it fundamental harmonics? Why we call it fundamental harmonics? Yes, then you didn't answer last 2 questions. Today your sound is a bit low, looking a bit tired, perhaps. So why we call it fundamental in physics? The word fundamental means the base. Remember the 7 base quantities, we call them fundamental. The charge of an electron is called the fundamental. Fundamental means something which start the zero ground position. So this is the first pluck. This is the first vibration. Now look at this thing. There are 2 loops. It is called first overtone. This is called first overtone. A very famous thing comes here, that this is the case number 2. Now, how come L is equal to lambda? Because across the length of the string, there are 3 nodes. Across the length of the strings, there are 3 nodes. There are 3 nodes, lambda by 2, and you can look at this screen. This is called first overtone. There are 3 loops now. This is called case number 3, second overtone. Why L is equal to 3 upon 2 lambda? Why L is equal to 3 upon 2 lambda?
There are 3 successive node-to-node loops here.
Actually, there are total separations are 3, but there are 4 nodes. There are 4 nodes in between the lengths, so the gaps are 3. So that is why we put lambda by 2, lambda by 2, lambda by 2 3 times. That is why it is actually this case. This is actually this case, and the string is vibrating between the string is vibrating between the 2 positions. So we can produce multiple loops, and we can get them. We can produce multiple loops, and we can get different output of vibration. Stationary waves in microwave. I put an easy question here. What are microwaves? Yes. What are microwaves? Microwaves are man-made electromagnetic waves. These are low frequency electromagnetic waves. So we can produce them. We can say that these are our discovery, and we made it. Microwaves are famous for their communication purpose in mobile phones and other things. Now I have a reflecting sheet. I have a probe and a meter, and I have a microwave transmitter. Every mobile is like a microwave transmitter. Now I generate the signal, and the signal goes forward and rebounds. The signal goes forward and rebound. Now this is called the formation of a stationary wave. The signal goes this is the incident signal. This is the incident signal, and the wave returns. The wave returns from the reflecting surface, and due to superposition of the 2 waves, due to superposition of the 2 signals, a stationary wave is established. This was the apparatus, microwave transmitter, a probe, and a reflecting surface. Now we establish a stationary wave. Then what was the procedure? That how we determine the wavelength? we have to move the probe along a meter rule, and we will detect successive nodes and antinodes. We will detect successive nodes and antinodes by the meter. The meter will detect maxima or successive minimas, node or antinode. Now we have to find the distance on the meter rule between two successive nodes or two successive antinodes. If we double that distance, it is called wavelength. Now this is the apparatus. We move it slowly across this meter rule. The output, if you are connecting a CRO, you will get this idea that the node, antinode, node is the zero intensity and antinode is the full intensity of the signal. So we'll get a graph like that. Determination of the wavelength of sound by a standing wave. Now this is the apparatus. Sound signals are longitudinal signals. We have a loudspeaker, we have a closed-end pipe, and we have placed some dust particles in it. Look at this apparatus. Look at this apparatus, and I'm going to ask you how it works. Okay, now how this apparatus works.
Sir, I think I saw this time seen it before.
Actually, can't hear you proper today. Can you repeat that? That we have this apparatus, we will switch on the signal generator, and a sound pulse will produce. It will reflect from the closed end and a stationary wave is produced. Why the heaps of sound will be produced? Because the sand particles will be taken off by the sand particles will be taken off by the signal, by the waves, and they produce heaps of sound. They produce heaps of sound. The dust particles will be suspended on equal distance positions, which are the nodes. This is the apparatus to show that you measure the separation between two heaps, and that distance is called lambda by 2. Double that, you will get the wavelength. This is the second method, CRO method. Now you have a loudspeaker. Loudspeaker is connected with a signal generator. Loudspeaker is connected with a signal generator, and the signal generator will produce sound signal. It will be producing sound waves which reflect from the plane surface. Again, the same procedure. The microphone, the probe is the microphone. The microphone is moved slowly along the meter rule. The microphone is moved slowly along the meter rule. We will notice the two successive maxima, loud sounds, or two successive minima, the low sounds, and then you will find the separation between them and double that separation. If you double that separation, that will be the wavelength. The same logic, you have to double the separation because it is lambda by 2. Now, loudspeaker runs by a signal generator. Signal generator is like a frequency controller. Signal generator is like a frequency controller. And this apparatus signal generator is like a frequency controller, and it produces signal of high frequency. Now this is the screen. Node, antinode, node, antinode. Stationary or standing waves in air column. What was that topic? Air column. There are two types of air columns. One is called open pipe and the second is called closed pipe. There are two types. Closed pipe, open pipe. This is called a closed pipe. In a closed pipe, what happens? The sound waves are coming down, they rebound from the closed end and they superimpose to form a stationary wave. Achha, when you have a closed pipe, there is always a node on the closed end and there is always an antinode on the open end. Look at this derivation. Now it is node to antinode, it is node to antinode. So it is lambda by 4 because node to node is lambda by 2. We use the formula to find the frequency. Look at this small derivation. So this is a derivation which is always there. Now, this is called the fundamental harmonics. This is the primary tone. This is the first tone. L is equal to lambda naught upon 4. Now, if I vibrate it in two loops, in 1.5 loop, then node to node is lambda by 2, but node to antinode is lambda by 4. So the total is 3 upon 4 lambda. This is the first overtone. And we can continue in the same way, and we can continue if there are 2.5 loops. Then L is equal to 5 upon 4 lambda. This is a very important feature in the exam, how you can connect length and lambda. And correction, it has been removed from the syllabus last year 2022 and it is not there. What was it? It's necessary to see what is there. It was a slight edge above the open end of the tube. And these were the formulas. You should know that they are not in the course. Open pipe. This is another musical instrument, trumpet, etc. It is open for both sides. Now, in an open pipe, the two signals meet and they superimpose. The two signals meet and they superimpose. This superposition establishes a stationary wave. This time, there are two antinodes on the two open ends. The rule is the same. Antinode to antinode, it is lambda by 2. You have to count the node and antinode and you have to relate length and lambda. You have to relate length and lambda. And correction, this one is not in course as mentioned earlier. And correction is not in course. Now, air column above water. Why water? Can anyone tell me that why water is discussed, why water is used as a medium in musical, so-called musical setup? Water is a soft medium. Water is a soft medium. And when waves strike water surface, they produce a soft sound. This is why we use them. Now, this is the medium of water, and I have a tuning fork. The tuning fork is vibrated on it. The signal goes down and signal comes up. This is our air column above water. Water is actually closing the pipe from the bottom. The approach is the same, that sound waves are produced, but why they are softer sound? Why they are softer sound? Because why they are softer sound? Because they are coming from the water. They are reflecting from the water surface. Comparison between progressive and standing wave. Now, this is a very good topic, and normally people ignore this topic, but it creates some problem. Many people forget it, these important comparison, and I think I had posted it on my notes posting job, and I had posted this. Now, look at this table. Energy is transferred. I'm reading from the left. Energy is transferred along the direction of propagation. Now, stationary waves, no energy is transferred. All points are important, but the last one, neighboring points are not in phase. Here, all points between two successive nodes vibrate in phase with one another. That is why the famous question comes that what is the phase difference between 2 points between two nodes? The answer is 0. Why it is 0? Because the neighboring points are exactly in phase. You have to read these 2 points and ask any question you want to ask here on this sheet.
Sir, can you explain what is the neighboring points for the point? Progressive waves, the part 5.
The neighboring points are not in phase का मतलब है कि progressive wave तो वापिस ही नहीं आती. The progressive wave is not coming back. तो इसलिए जब आप एक progressive wave बनाते हो, look at the progressive wave. It's moving like this. It's going forward. Every particle then will go up on its turn. Every particle go up on its turn. तभी wave थोड़ी देर के बाद इधर आ जाएगी, फिर थोड़ी देर के बाद इधर आ जाएगी. ये जो वेव है ये बिल्कुल रिले रेस की तरह चलती है लाइक दिस. यानी वेव आगे कैसे जाती है? that every particle go up on its turn. यहां पर ये लूप बन गया. अब जो पार्टिकल इधर है, अब अगर कोई पार्टिकल इधर है तो वो इधर ही रहेगा. इट इज जस्ट ऑन इट्स पोजीशन हियर. So it is exactly in phase because the particles are not all the particles are not making the crest in our stationary wave. All particles do not make the trough. अब जो पार्टिकल इधर नोड पर बैठा हुआ है, ये वाला देखो पार्टिकल, लेट इट कॉल पी, ये हिलेगा ही नहीं, ये हमेशा जीरो पे रहेगा बिकॉज इट इज अ नोड. सो फर्क ये है कि स्टेशनरी वेव में हर पार्टिकल का रोल फिक्स है और वो दूसरे जैसा जरूरी नहीं है. अच्छा, प्रोग्रेसिव में क्या होता है? एवरी पार्टिकल विल गेट अ टर्न, it will become the crest, it will become the trough. That is why उनका फेज में हो ही नहीं सकते, क्योंकि हर पार्टिकल ऊपर भी जा रहा है, नीचे भी जा रहा है. हर पार्टिकल is going up and going down also.
Thank you.
Now look at this screen, that this is node to node, and this is a very important concept. Node to node, the phase difference is pi radian, and the difference lambda is 2 pi radian, 1 lambda. Now, important phenomena of waves. The important phenomena of waves, I will like to recall actually all the phenomena which we have studied, some of them in our O-level also, and their names are there. Reflection, refraction, dispersion are coming from O-level, are only a memory that these are some phenomena also. This diffraction and interference are the AS level 1. This is called reflection. This is called refraction, and this is called dispersion. Diffraction. What is diffraction? Okay, look at the diagram and give me the definition. What is diffraction? Diffraction is the bending of a wave. Diffraction is the bending of a wave as it passes through a narrow slit. So what is diffraction? Diffraction is the bending of a wave. Diffraction is the bending of a wave as it passes through a narrow slit. This is bending. During diffraction, lambda does not change. Look, this is diffraction. Waves are bending, but lambda does not change. Lambda must remain constant during diffraction. This is diffraction. What is the second definition? I show you the diagram and you can tell me now what is the second definition. Yes, what is the second definition? Yes, anyone? When waves come across an obstacle, like you put a stone in the flow of water, and the water waves disperse, and the water waves split over the obstacle. Water waves will eventually meet. Water waves will eventually meet as they move forward, but some waves, like light waves, do not meet after this split over, and this is called a shadow region. Degree of diffraction, the formula. Degree of diffraction is a measure of degree of bending. How much the waves bend. Degree of diffraction is proportional to lambda upon W. Lambda wavelength and W slit width. Look at this screen carefully and absorb it. lambda red, lambda blue. Look at the color difference. So red color wave is bending more than blue. Why red is bending more than blue? Why red is bending more than blue? Because the wavelength of red is greater than the wavelength of blue. This is called the slit width. Look at this. This is called slit width. So if the slit is narrow, bending is more. And if the slit is wide, bending is less. Okay. When we want to show the crest, we have to draw continuous line. And when we have to show the trough, we draw dotted lines. How we measure lambda on a wavefront diagram? We draw parallel lines, the tangents, and we draw tangents to find the wavelength. Diffraction and intensity. Diffraction means spreading of wave. When a wave spread out, amplitude decreases, intensity decreases. So diffraction decreases the intensity of a signal. Look at this screen. This is diffraction is happening. And due to diffraction, the signal is getting weaker. The signal is getting weaker. Look at this screen. Diffraction in water waves. These are the water waves entering a type of section. There is a bending of wave. This is famous ripple tank, and we have placed a boundary. Ripple tank can be having a dipper which runs by a signal generator, and you can see the slit is introduced for diffraction. Now, this is the top view and for the ripple tank, and the waves are passing through this narrow slit. The waves are bending over the slit. Interference. What is interference? Interference is the meeting of two coherent waves moving in the same medium with the same speed. Coherence. What is coherence? Coherence means same nature, same wavelength, and constant phase difference. So if two waves are identical in nature, they have the same phase difference, they are moving in synchrony with each other, they are called coherent. Now, coherence is a very important condition. Whenever interference comes, this is their favorite question, coherence. Look at this screen, exactly in phase. We did this topic in waves. The waves are moving in synchrony with each other, and this is called constant phase difference. This is called exactly out of phase. So these are the three signals back to back. This screen is called exactly out of phase. Conditions of interference, the primary condition, coherence, same medium, same speed, meet at a point. Now, why it is necessary then that coherence is there? Otherwise, no interference can occur. Yes, you can hear me?
Sir, if waves, am I audible? Can you hear me, sir? Hello?
Yes.
Yes. Sir, if sources are not, if the two sources are not coherent, then they won't be able to produce waves?
Superimpose. Just like
Yes.
the example of two hands again. So remember that interference is an application of the principle of these are the conditions of interference, and we were discussing then if they are not coherent, they won't meet each other side to side. Actually, if they are not coherent, they are just like two different sizes. So when you suppose put a cap on a bottle head, the cap and bottle should be coherent. If they are not of the same size, the cap won't fit over it. So interference is an application of the principle of superposition. So they actually do not meet until they are superimposed. So if the waves are of different sizes, superposition is not possible. So look at these two signals. I draw two signals. One is this, and second is this. No superposition, no interference. The two waves are not coherent. So what is the concept? The waves are coherent, so they can superimpose. When they superimpose, then they can interfere. There are two types of interference. As in our common life, there are two types of interference. One is called constructive interference and second is called destructive interference. In destructive interference, amplitude becomes zero ideally, and in constructive interference, amplitude doubles. But these are additional conditions. Waves meet exactly in phase. For destructive, waves meet exactly out of phase. A very important sheet to be remembered, that if they are meeting in this way, the antinode and node will be formed on constructive and destructive interference respectively. So please absorb this sheet. Now look at this diagram, A plus A, 2A, constructive interference, constructive A plus A, 2A. Now, this is not always the case. This is an exception. Now look here, the two amplitudes are already different. This is also a type of constructive interference. Now here, one is A and one is minus A. They are meeting out of phase. They are meeting out of phase. So this is an example of destructive interference. Meeting exactly out of phase. So they are getting zero. Look, this is node. Again, it is not necessary that always it is zero. One is a wave with A1, second is A2. This is not a node, but it is a destructive interference. There are two types of sources, point source and extended source. Now look at this very important diagram and look at the diagram. There are dotted lines, trough, crest, and this is the bit better version of the same diagram. Remember, the continuous lines are crest and the dotted line are trough. I will ask one simple question. Look at this diagram carefully. Now, when waves are moving successively, why there is a node? Why there is a node on point P? Why there is a node on point P?
Because they're out of phase, so they're destructive. There's destructive interference. So that means it's to node. It's
Very
node.
Okay, now then why there is an anti-node on position Q?
It's because it's a point.
Sorry, can you repeat?
It's a point where both of them are meeting.
But are they, look at the position Q now, look at the position Q. Are they on the position Q, are they both crest or trough? They both are dotted.
Yes, sir. Both are troughs.
So both are trough. So it means when trough to trough meet, when trough to trough meet,
An antinode is formed.
yes. Now this is a very helpful concept map. Trough plus crest gives you exactly out of phase, destructive interference, and node. This is crest plus crest or trough plus trough. इसमें देखो क्या बना, that it's a constructive interference and it is a case of anti-node. Intensity is maximum. Crest plus crest, trough plus trough. So exactly in phase, constructive interference. Now, if we join all the nodes, we get a nodal line. If we join all the anti-nodes, it is an anti-nodal line. Interference pattern, they meet back to back. It's a sequence of maxima and minima. When waves interfere, they produce a sequence of maxima and minima. What is maxima? It is a constructive interference. What is minima? Destructive interference. Look at this nice animation. This is an example of interference. Interference in sound waves. What is the output when sound waves interfere? They produce a series of high and low sound signals. Low signal means antinode and no signal, silence means node. Interference in light waves. Maxima means a bright fringe and minima means dark fringe. Look at this diagram. This is a typical interference pattern in light. There are some dark regions and there are some bright regions. Dark region means destructive interference and bright region means constructive interference. Path difference and phase difference, a very important topic. Remember that 1 lambda always corresponds to a phase difference of 2 pi radian. This is a very important concept. Now, two waves are coming from S1 and S2 and they meet at a position P. They are coherent waves. So when they meet, they travel a distance. So path difference is generally shown in terms of lambda and it can be converted into phase difference. What is path difference actually? You can show it by the difference of the distance traveled. Look, the one wave has traveled 6 meters. One wave has traveled 6 meters and the other wave has traveled 10 meters. So the difference is 4 meters. We can convert it into lambda. In terms of lambda, so it is 2 lambda. And we can convert it into phase difference also. So look at this calculation. You can convert the path difference into phase difference also. PD. PD is either in terms of pi or PD is in terms of lambda. Now, this is the example number 2. Two waves, S1, S2 are the two sources. Waves are coming and they have traveled the same distance. Now, the path difference will be 0. The path difference is 0. The phase difference will also be 0. One wave is 2 meter, lambda is 2 meter. One wave has traveled 7 meter and other wave has traveled 10 meter. If you subtract them, 3 meter. Look at the separation. It is 3 upon 2 lambda. I have made as a fraction. Now, look at carefully the simple calculation for phase difference. Now, phase difference is coming 3 pi radian. So now we make a very important rule discussion that constructive interference path difference is always n lambda. N is equal to 0, 1, 2, 3, and lambda is equal to 2 pi. So the phase difference will be even multiple of pi. This sheet is very important to learn the formula for path difference. So please look at this sheet. I'm just coming. Look at this sheet. Conditions of constructive interference. Waves meet in phase. Zero phase difference. Mein. Part difference is an integral multiple like 2 lambda, 3 lambda, 4 lambda. Phase difference is an even integral multiple of pi. Resultant amplitude is 2a or magnified. A very important sheet. Just try to absorb it. For destructive interference, it is n minus half lambda, or PD is equal to n plus half lambda. N plus half is not common, n minus half is always there, but this time n is not equal to 0. N is equal to 1, 2, 3. So whenever you put it, you will get non-integer lambdas, 3 upon 2, 1 upon 2. But this time, the phase difference is an odd integer for odd integer of pi. Again, conditions. For destructive interference, the wave meet out of phase. Part difference is a non-integral multiple of lambda. Phase difference is odd number, 3 lambda, 3 pi, 2 pi. Resultant amplitude is 0. Amplitude this time decreases. Now, this is a concept we were discussing few days back when we were when we were discussing this question. That when waves interfere in this pattern, they produce bright and dark fringes back to back. It is a typical interference pattern. Interference in water waves using two sources. Now, this is a ripple tank and there are two dippers. Two dippers are being run at the same frequency and they must be coherent, constant phase difference. Now you can see the pattern, dark and bright fringes. Water waves are producing this image on the sheet below the glass block. Look at this. Interference in water waves using two slits. This was a remarkable idea when scientists were in a trouble that how to get coherent signals. It's always difficult to get coherent signals because signals slightly vary always. So an idea came up that why don't we use a single source with two slits? When you use one source with a double slit, coherence is possible. Now look at this screen. It's a single dipper with a double slit. Originally, it is a single source. There are two slits ahead. So when the waves come, they split over. Originally, they are the same wave, but as they divide, they give coherence. So smaller the lambda, smaller is the width of the slit. For light rays need very narrow slits. Interference in microwaves using two slits. Now this idea got successful. So then they tried double slit in every source, like microwaves as a double slit. Now the same idea, it's a single microwave source and a double slit is there. So when we put the interference, we get a pattern like that. The central fringe is bright, high intensity, and the intensity drops sideways. Now comes interference in light. Interference in light is a difficult topic. It was from the start, it was a challenge for scientists. Why it was a challenge for the scientists? Why it is difficult to get interference in light? Because light rays are so short in wavelength that it is never easy to get interference in them. So that guy, Young's experiment got the success first time, and he used the same idea that he used a double slit. He used a double slit. He used a double slit in order to generate the wave pattern, the interference pattern. So Young's double slit experiment was conducted. It's a single source. Look at the source, and two waves are coming out of the single source. This is a single source and there is a double slit. The waves are interfering. The light from the two slits form a visible pattern. The pattern consists of a series of bright and dark parallel bands called fringes. Constructive interference occurs where a bright fringe appears, and destructive interference results in a dark fringe. This is originally a single source, but a double slit. So one source becomes two wavelets. We can use trigonometry here to find the angle. Look at this diagram. It's a laser and light is passing through a single slit, and then we are breaking it in that pattern. It is originally a double slit and lights are spreading. This is a double slit monochromatic light, and it is going forward. The central maxima, central fringe is very bright, and the brightness decreases sideways. We number it. N is equal to 1, N is equal to 2, and then we number upward also. N is the order. So look at this screen and absorb it. You have to observe this screen, and I'm just coming. Look at this pattern. This is a double slit, and when wave passes through the double slit, they meet at a point. This is called interference. Look it again. The central fringe is very bright. The central fringe is very bright, and the brightness or intensity decreases on both sides. This is the pattern. The central fringe is very bright, but intensity decreases on both the sides. So this is, we are talking about Young's double slit experiment. We're talking about Young's double slit experiment, and this experiment was conducted in order to show interference in light. Look at this diagram. A is the slit separation, D is the screen separation, and X is the fringe separation. Look at this important formula. Determination of wavelength of light. How we determine it? This is the apparatus. And we use an eyepiece to determine the X, the A, everything. And this is the same screen, and this is the formula. We rearrange the formula. We rearrange the formula to find lambda. We put everything, and then we find lambda. Factors affecting the interference pattern. Look at this diagram third time. And the first factor is there. If I keep lambda and d constant, X and A are inversely proportional. So if we alter the slit separation, fringe separation changes reversely. Normally A is very small. Now look at this idea that when the value of A is small, fringes are far apart. When A has increased, fringes come closer. So when A is increased, X decreases. So we can use this formula. If one slit is closed, these are the double slit ones. Now, if you close one slit, only diffraction occurs, but proper interference won't occur. X and D. What is X? Fringe separation. What is D? Screen separation. So X and D are directly proportional. X and lambda are also directly proportional. Degree of diffraction is lambda upon W. Now, it means when you alter the lambda, like with color change, if you increase the lambda, degree of diffraction increases. So brightness decreases. So like red color output screen is a bit fainter. Look at this screen, very technical, but very important to remember. Width of slit, like the blinds on our windows nowadays, when you open the blinds, the width increases, more light will enter, and also degree of diffraction changes. When width is greater, when you open the blinds, more light will pass, less spreading, small envelope. Diffraction in waves, diffraction grating. Now we are towards the end of this heavyweight chapter. What is diffraction grating? Look at this. This is a diffraction grating, a thin sheet, and we have number of lines on it. This is like a sticker line, and this is a thin glass sheet, and we have printed close lines, very close, like a barcode. The lines are very close. In a diffraction grating, it's a multi-slit apparatus. It's originally a double slit apparatus, but with multi-slit option. Now, all the fringes are equally bright. A number of fringes are there, and all the fringes are bright. Intensity this time does not decrease. It's nearly the same. Now, there is a concept of angle of deviation, angle of bending. So the wave bends over and below the central fringe, and this is theta. Formula n lambda is equal to d sine theta. N is equal to fringe order, d is equal to slit separation, theta is equal to angle of deviation. This is a combined formula. Now, d is the separation between two slits. D is the separation between two successive slits. The same as A in Young's double slit. D is equal to 1 upon n. N is the number of lines per meter. The very common mistake, people do not multiply by 1000 because lines are given per millimeter. But you have to convert them for 1 meter. N is equal to number or order of diffraction. N is maximum when theta is 90. This is a common case in this chapter. N lambda is equal to D. Now, why theta is 90 for max? If you move these rays till 90, they will be parallel, they will be upward. No more diffraction would be possible at beyond 90. Now, n is always a whole number and you always round it backward. Look at this rounding. N is not the total number of fringes. Total number of fringes is 2n plus 1. Why? Because if you look at the zero order, 2 fringes above zero order, 2 fringes below. So including the zero order fringe, there are 5 fringes. Grating works when the incident light is perpendicular to the grating. So the path difference is 0. So if the rays are coming at an angle, there would be a problem and answer won't be accurate. One-way grating. This is called one-way. Vertical grating lines are producing horizontal pattern. Horizontal grating lines produce a vertical pattern. And two-way, like a mesh, laser, a two-way grating, and a screen. This is how a two-way grating looks like. So when you produce an image, it produces an image like this. This is a two-way grating image. Two-way grating, in a two-way grating, the screen produces horizontal fringes and vertical fringes. D is inversely proportional to N. So fringe separation increases if you alter the D. This is the formula. Now, if you increase the lambda, fringe pattern fades. Diffraction of white light. Diffraction of white light is there in the central fringe is always white. The central fringe is always white. Look at this one. But the fringes above and below, they break up in color because white light actually consists of 7 colors. The approach here is lambda is proportional to theta. In a white light, there are different lambdas. So they bend on different angles. So they bend on different angles. This break the pattern in different colors. Normally, red color lambda is greater than violet. So red color theta is greater than violet. So that is why central fringe remain white, but the sideways fringes get in 7 colors. Look at this pattern, 7 color breakup. The very good example of diffraction is a CD. If you move the CD in light, if you move a CD in light, you will see 7 colors on the CD. Well, this is the end of this heavyweight chapter. And we have, mashallah, revised it, the whole chapter, everything. And now it's better to stop the class because we have to do questions, but we can do it in the next class. It's over for today. Thank you. Allah Hafiz.